All right, today we're going to peek behind the curtain at one of the most fundamental choices in all of computer programming: how to handle a simple list. I know, it sounds super basic, right? But trust me, this one decision can be the difference between an app that feels lightning fast and one that's just painfully slow. I mean, just think about it for a sec. Your phone's contact list, that Spotify playlist you're always adding to, your never-ending social media feed, at the end of the day, they're all just lists. So how does the software behind the scenes handle all that, letting you scroll and add and delete stuff in like the blink of an eye? Well, it's definitely not magic. It all comes down to a fundamental choice between two different ways of organizing that data. And we're going to break that choice down right now. Okay, first up, we've got something called the array. And honestly, the best way to get your head around an array is to just picture a sturdy, perfectly organized bookshelf. See, an array is basically a single, continuous block of computer memory. Just like a bookshelf is one solid piece of furniture, right? All the items, our books, are stored right next to each other in numbered slots. And here's the key part: the size of that shelf is fixed from the moment you build it.
And it's this exact structure that gives the array its superpower, just incredible speed when it comes to finding things. It's called random access, and here's how it works. Because all the slots are the same size and they're all sitting right next to each other, if you want the book in, say, slot number 7, the computer doesn't have to look at slots 1, 2, 3, and so on. Nope, it does a super quick calculation and jumps directly to that 7th slot. Boom, access is instant. It's just like grabbing a book when you know exactly where it is on the shelf.
Okay, so that speed is amazing for reading data, no question. But what happens when the list needs to change? What if you need to add a new book to your perfectly organized, completely full shelf? This is where the array really shows its weakness. Because that block of memory is continuous and totally fixed, you can't just, squeeze a new item in at the beginning. No way. You literally have to build an entirely new, slightly bigger bookshelf. Then you have to painstakingly move every single book from the old shelf over to the new one just to free up that one empty spot at the front. I mean, it's a huge, slow, and super inefficient operation. So that massive inefficiency brings us to our second solution, which takes a completely different approach. This is the linked list. And for this one, I want you to forget the bookshelf. Instead, picture a train. So a linked list isn't one big, solid block of memory. It's more like a series of individual items, or nodes, that can be scattered all over the place in the computer's memory. Each node is like a train car. It holds a piece of data, but, and this is the crucial part, it also holds a link that points to the exact location of the very next car in the train. And this chain structure is what gives the linked list its own superpower: incredible flexibility. Remember how painful it was to add an item to the front of our array bookshelf? Well, with a linked list, it's unbelievably easy. You just create your new train car, you connect it to the old engine, and then you just announce, hey, this new car is now the engine. And that's it. No moving everything else around. It's fast, it's efficient, it's kind of beautiful, right? But of course, there's always a trade-off. With all that flexibility, you lose something else. You can't just jump to the 7th car in the train anymore. There's no index, no easy way to calculate its position. The only way to find it is to start at the engine and walk through each car one by one. Car 1, car 2, car 3, all the way until you get to the one you're looking for. This is called sequential access. And yeah, it can be a lot slower than the array's instant random access. So there we have it, two very different ways to do things, each with its own awesome superpower and its own distinct weakness. Let's put them side by side for the final showdown. And this really gets to the heart of the trade-off. The array, our bookshelf, is an absolute champion at reading data quickly, but it's rigid, it's slow to modify. On the flip side, the linked list, our train, is the master of change. It's super flexible, but it's way slower when you need to find one specific item. The choice gets even clearer when you look at these key operations. If your main job is just reading data based on its position, yeah, an array is the clear winner, hands down. But if your list is constantly changing, if you're always adding and deleting things, especially at the beginning, a linked list is the obvious choice. Okay, so this is all cool from a technical perspective, but why does this choice between a digital bookshelf and a digital train actually matter to us, as the people using the apps? Well, it really brings us to the ultimate question. After all of this, which one is actually better?
And the answer is the classic and honestly the wisest response in all of engineering. It depends. There's no single best data structure. There is only the right tool for the right job. So you'd use an array, the bookshelf, for something really stable, like an application settings. You load them up once, and then you just read them over and over. But for something like a social media feed, where new posts are constantly being added right to the top, that's a perfect job for a linked list, the train. It's also great for something like a text editor's undo history, which is constantly growing and shrinking with every keystroke. So I'll leave you with this thought. The next time an app on your phone feels incredibly snappy and responsive, or maybe frustratingly sluggish, just ask yourself, could the reason for that feeling be as simple as a choice a programmer made a long time ago? The choice between a bookshelf and a train. Thanks for tuning in.